Welcome. Today we'll be discussing section 2.2, rotation angles, coterminal angles, standard position, as well as some identities. So in the past, we have learned about geometric angles, and with those, we had two rays, and we had an inner angle as well as an outer angle. Rotation angles are going to be much the same, but now we're going to add that we're going to rotate a ray to another position. So imagine I still have my two rays, S and T, and now instead of just fixing them and just saying, here's an angle, we're now going to say, how can we rotate S to become T? Well, there's clearly two different ways that we've already discussed: an inner, which we can denote as alpha, and an outer, which I'll denote as gamma. Now, we have to also orient what direction we're rotating. And so we denote counterclockwise as positive, this is the abbreviation for counterclockwise, and negative is clockwise. Counterclockwise for a face clock is this way, and clockwise is this direction. So I can imagine, let's just say that I spun this angle S, I spun it 130 degrees. So that means in the clockwise direction, I went 130 degrees. So alpha equals 130, let's do 35, 135 degrees. Now, if I were to say rotate this 135 degrees counterclockwise, and then I didn't stop here, I instead came back around and landed here, this would be that my gamma is basically 135 degrees minus 360 degrees because I went back I went back in the clockwise rotation. Okay, so adding those together and we get negative 225 degrees. All right, well, what if I have now a beta angle where I start at S, I rotate it to T, but then I go around one more time and denote this as beta? Well, let's track that. Beta equals 135 degrees plus 360 degrees, which when we add them together, we get 495 degrees. So we have to have a way of describing the starting position and the ending position and have a way to generalize what are all the possibilities to get from the starting to the ending position. So we denote this as the starting, that's why we call it S, and we call this T because it is the terminal side, meaning that the process terminates or we stop there. So whenever we have these angles that start in the same position and terminate on the same position as well, we call those coterminal angles. Now, how can we describe all coterminal angles that are equivalent to this alpha? meaning that they start and that they end in the same spot. Doesn't matter how many times we spin around the circle. Well, we can say that 135 degrees plus 360 degrees times n. This would be all of the angles possible. And when we look at this, n is an integer, and so that means we can have all the negative and all the negative, like -1, -2. We could also have 0, 1, 2, 3, 4. So if we plug in 0 here, that cancels out and we get 135. If we plug in a 1 here, then we can add these two together, getting 495. And if we put a -1 in here, we have 135 minus 360, which is -225 degrees. So in essence, all of these angles that are written here are equivalent. They're the exact same. And this is how I can get from one angle to another. To highlight this, what are three equivalent angles to, let's do pi over 3. So now we're working with radians, and this concept works with radians. So let's first find out what our formula is. So we're going to have pi over 3 plus 2 pi times n. And now we just want to find 3 coterminal angles. So let's try. If n equals 1, then pi over 3 plus 2 pi times 1, well, that's equal to pi over 3 plus 6 pi over 3. So that's 7 pi over 3. Okay. Well, so that's one coterminal angle. Well, now let's try if n equals -1. We should find something similar, because then we have pi over 3 plus 2 pi times -1. Well, that's really pi over 3 minus 6 pi over 3, which then that would equal -5 pi over 3. And now we could find the pattern for the last one. If we have, let's do it over here in this box. If n is equal to, let's say, 2, then pi over 3 plus 2 pi times 2. So we have this pi over 3 plus 4 pi. Well, we want something to be, we want the common denominator, so I'm going to times the top and bottom by 3. So we have 12 pi over 3. So that gives us pi over 3 plus 12 pi over 3, which is 13 pi over 3. And so, box on our answers, these are 3 coterminal angles to pi over 3. Okay. So now we want to have a standard way of talking about these angles. And so this gives rise to the notion of a standard position. So a standard position is two conditions. One, the initial side coincide, meaning we start at the same spot. And then two is we rotate about the origin. Meaning what we do, oh, sorry, I want to mention one thing, that the initial side coincides with the positive x-axis. So meaning that when we draw a graph, we're always going to start here. We're always going to start on the positive side of the x-axis. And we're going to rotate from there. Where? From the origin. This way, we can define a new coordinate system from there. We can also don't have to be like, oh, did we start here? Did we start here? Did we start here? We can just orient everything from the same spot. So from here, what we can do is we can use a geometric way of constructing and calculating angles. So say I had a point, say I had a point P, which was -8/17 and 15/17. We've constructed the unit circle and we know how to calculate angles on the unit circle. This point lies on such a circle. So we take this point and when it's about, let's do about here. So that is -8/17, 15/17, and so it forms like a circle, sort of like that. So we want our terminal side to intersect or contain this point P, meaning we have an angle such as this. Let's call it alpha. And so what we can do from here is we can construct a geometric angle because we know that from here to here, in other words, the positive x-axis to the negative x-axis, we know that that's one turn. So say that that is 180 degrees. So we know that this is kind of what's left, and we don't really need to know the side or this precise angle here because our geometric construction allows us to create a triangle here. A triangle with what? Well, we know that the radius is 1. We have a side of 8/17 and another side of 15/17. And we can check our math real quick and add these together to get 1, or with Pythagorean's theorem, I should state. But from here, we can now, with this, I'll call it theta, we can now calculate all the trig values. So we can say that sine of theta is equal to, and we're going to have opposite over adjacent, so that's 15/17. Sorry, opposite over hypotenuse. I don't know why I said that other thing. Cosine of theta, and we can write this as 8/17. And some of you might be saying, hey, I'm using a positive notation. Well, I'm using a positive notation because our geometric constructions are required to be in positive lengths. But we know this is on the negative side of the board, so we can state that this is a negative 8/17. We also can use tangent. Tangent of theta will be sine over cosine. And so we'll be able to calculate that and get -15/8. And finally, we can calculate the rest. So we can have cosecant of theta equaling 1 over sine, so that's 17/15. Secant of theta is 1 over cosine, so that's -17/8. And cotangent of theta is 1 over tangent of theta, and we get -8/15. And so now we have formed all 6 trig values from this theta. Now we can insert our alpha into each one of these. But now I want to ask, what if we don't have something on the unit circle? What if we have something that's off the unit circle? Well, what ends up happening is we can now generalize our formulas. So we can say that cosine of this alpha is equal to the x value over r. Secant of alpha is 1 over cosine, so that's r over x. Sine of alpha equals y over r. And cosecant of alpha equals r over y. And the last two, we have tangent of alpha equaling x over y, and cotangent of alpha equals y over x. So how is this true? Why can we generalize this? Well, let's look back at our triangle. We had a triangle here that was 15/17, 8/17, and 1. Well, what's to stop me from expanding this triangle? And now I have a larger triangle with a radius here that is, let's call it 2. So from here to here, it's now 2. Well, how does that affect the other proportions? Well, it increases them by that same factor of 2. So if this was 2, then this side length here, that would be 30/17. And this side length here, this side length would be 16/17. And we can throw this into the same calculations and we're going to get the exact same results as before. So now we can make our trig functions into any sort of circle, not just the unit circle. And we now have a very generalized formula for them. So I've mentioned this a couple of times. I've been using them, and now we can properly define them as the important identities, and these are worth knowing through and through. I will star the ones that are explicitly important in my eyes, but if you were to memorize all these, that is good. These can be found on page 72 of the textbook. And for your check on learning, it will be to copy verbatim all of the trig identities on this page of the textbook. If you have not looked at the textbook before, you can find that on the syllabus. There will be a link to the PDF of the textbook. So what are they? We have some categories. The first is the reciprocal identities. And what they are is we have secant of alpha is equal to 1 over cosine of alpha. We have cosecant of alpha is equal to 1 over sine of alpha. Tangent or cotangent of alpha equals 1 over tangent of alpha. Now you get all the other identities back as well, so I can state that tangent of alpha equals 1 over cotangent of alpha, and cosine of alpha equals 1 over secant of alpha. And for completion, sine of alpha equals 1 over cosecant of alpha. However, I'll say that these three are the ones to memorize, because what can I do? I can take the reciprocal of the equations and I just get a copy of the ones down below. Now, you might be wondering, well, how can I memorize what pairs with what? Well, a trick that I kind of learned is there's one co per pair. So we have cosine and secant. Cosecant, sine. Cotangent, tangent. There's one co per pair of these identities. Again, for your check-in learning, it would be to write down all these identities as well as the other ones I'll show you, but the full check-on learning is to write down all the identities in this page of the textbook. It is extremely important to know these. So the other set is the ratio identities. And so for these, you'll have identities like tangent of alpha equals sine of alpha over cosine of alpha. sine of alpha equals tangent of alpha over secant of alpha. And another one would be cotangent of alpha equals cosine of alpha over sine of alpha. The tangent ratio identity being the most important. Because if I have one relation between tangent, sine, and cosine, I can start making a whole bunch of relations. And really, all that the rest of these trig identities is we just use one set of identities, we apply another identity, and it just starts spitting out other identities. For instance, take a look at the sine. We have sine here being equal to cosecant. Well, what is cosecant? It's 1 over sine. Well, here I have tangents, and tangent is 1 over sine, or sorry, sine over cosine, and I'm dividing by a secant, which is 1 over cosine. So I can imagine that this is sine theta over cosine of sorry, this is alpha, all over 1 over cosine of alpha. Well, we times top and bottom by cosine, and we cancel, leaving us with just sine. Well, now I'm going to times by 1 over sine of alpha, 1 over sine of alpha, and cancel. I'm left with 1 over sine in the denominator. What's 1 over sine? Cosecant. That's by this identity. And so we just cycled an identity through, and we got something new. And we call it an identity. And there's several other ones. I want you to write them all out because I've done this a long time. I'm used to these different notations. I want you to be used to seeing cotangent as 1 over tangent, secant as 1 over cosine, cosecant as 1 over sine. Get used to these as you're going to play around with these identities. You will also have the product identities. I'm not going to write them here because all that we're going to do is take a ratio identity and we're just going to times it across. So here I have tangent alpha is equal to sine alpha over cosine alpha. Well, if I times each side by cosine alpha, I get cosine alpha tangent alpha equals sine alpha. I'm going to call that an identity. This is now a product identity where before it was a ratio identity. And I want you to see these similarities as you go through and write them. So the last set of identities that I'll write on the board is the Pythagorean identities. And we know one of them to be sine squared alpha plus cosine squared alpha equals 1. And this we derived in a prior video. We then divided by sine squared. So if I divide by sine squared, I get 1 plus cotangent squared alpha equals cosecant squared alpha. And then if I took the first one and I divide by cosine squared, I get tangent squared alpha plus 1 equals secant squared alpha. And that was simply through the fact that we knew what 1 over cosine was and what 1 over sine was. And if we have 1 over sine squared, well, then we have cosecant squared. And same thing with the other identities. So again, I want you to, for your check on learning this video, is to write down verbatim every single one of these identities found on page 72 of your textbook. Thank you for watching and have a great day.